Hello and thanks for watching. I'm Corin Gawith from the University of Southampton and Covesion, and today I'm going to talk about the development of magnesium-doped periodically poled lithium niobate ridge waveguides for field applications of quantum technology. As with any project, the work presented today is a team effort, and I'd like to thank the teams at Southampton and Covesion for the work I'm presenting, particularly Sam Berry and Lewis Carpenter. The motivation behind our work is a growing ecosystem of quantum research worldwide. It's estimated that over $20 billion of public funding is invested in quantum research each year, which equates to hundreds of quantum research groups and startup companies and a rapidly growing market opportunity for quantum enabling parts and systems. Most of this funding supports academic industrial collaborations with an emphasis on transfer of quantum sensor, computing and imaging techniques from the laboratory and into commercial applications, and in many cases optical systems form the backbone of this work. Our particular technology of interest is periodically poled lithium niobate, or PPLN, a nonlinear optical crystal that's widely used in quantum technologies. We are interested in PPLN because it has a high second-order nonlinear coefficient that can be tailored for generation of light from blue to mid-IR wavelengths, providing tailored wavelength support for atom traps, paired photon sources, and upconversion imaging. The techniques for making and using PPLN are well known, and you can look these up on Covesion's website. What I'd like to do is take you through a couple of examples of our recent quantum technology projects and how these define the targets for our research in PPLN. The first is a cold atom space payload, or CASPA. This was a £2 million Innovate UK project led by Teledyne e2v to create a 6U CubeSat gravitometer based on a rubidium magneto-optical trap for space-based gravity measurements. The application is environmental monitoring of polar ice mass and the underground water table for urban planning. The real challenges of this project were the limited 4U payload, so restricted size of the quantum system in the satellite. It's restricted to about 20 by 20 by 10 centimeters, a 40-watt peak power budget provided by the solar panels, payload mass of less than 4 kilograms for the entire system, and all the components must pass pre-space qualification for radiation, vibration and temperature. There's also the problem of long-term maintenance-free operation because you can't just pop up to space to retune your optical system. The PPLN needed in this case was to frequency double a 300 milliwatt space-qualified telecoms laser to around 40 milliwatts of 780. What you can see here is the final completed CubeSat package, which is about 30 by 20 by 10 centimeters in size. This incorporates a PPLN waveguide, telecoms laser, ion pump and computer control, and operates as a complete rubidium magneto-optical trap. It's been tested for vibration, radiation and thermal cycling. We're still seeking funding for an actual space trial. The next project is Pioneer Gravity. Similar to CASPA, this is a £9 million collaborative Innovate UK project led by RSK to create a field-ready rubidium MOT quantum gravitometer. The application in this case is site surveying. Digging in London causes around £1 billion per year disruption to hidden underground services such as power, telecoms and sewer lines, mainly because the city is so old that there is no real comprehensive map of everything that's underneath the ground. The challenges are that this must offer sensitivity advantage of the incumbent classical gravitometer systems that use a mass and spring. We need to identify voids and features several meters underneath the ground, and the thing needs to be portable for use in a field, literally in a field. So it needs to be transported by truck and survive the journey. The PPLN needed in this case is to frequency double a 2-watt telecoms laser to around 1 watt output at 780. The 1 watt power level enables the rubidium MOT to be cycled more frequently for a higher sensitivity measurement. What you can see here is an example gravity sensor developed by the University of Birmingham, which incorporates the full optical control and rubidium MOT system in a portable package. This system has been used in numerous field trials. These are literally done outside in a field looking for voids and objects several meters below ground level. What we get from projects such as these is a set of PPLN performance targets to meet the needs of our academic industrial partners. To summarise these, we're aiming for SHG of telecoms lasers converting from 1560 to 780 nanometers for use with rubidium atom traps. The PPLN crystals themselves need a rugged structure so they can be used in harsh environments of space and building sites and literally in fields. We need a high launch efficiency suitable for a fiberised package, because most of the people who are building these quantum systems aren't optical engineers. They just want something they can basically plug and play. Scalable manufacture, so we're aiming to be making hundreds or thousands of these things a month. High device efficiency and operation greater than 1 watts of 780 SHG output. Our approach to doing this is via zinc interfused ridge waveguides. Zinc is chosen to increase the refractive index and photorefractive damage resistance of lithium niobate. The aim is to create waveguides supporting watt level powers. As we want to make lots of these, our manufacturing process has been refined to 4 simple processing steps. We use periodic poling to give the crystal the appropriate grating structure for 1560 nanometer SHG. We then deposit a zinc layer around 100 nanometers thick for 1560 waveguides. The zinc is indiffused at around 1000 degrees to create a planar waveguide layer in the crystal, and finally the ridge waveguides and crystal facets are created using a high precision dicing saw. We do this processing at the wafer level and then break this down into multiple chips like the one shown in the diagram. You can get full details of the process in the reference paper. The machining process is at the heart of what we do. Our PPLN waveguide dicing is performed in the ductile regime, meaning that material is removed via elastic rather than plastic deformation. This dicing regime leaves a clean, smooth finish behind rather than the usual cracked and chipped edges associated with standard brittle dicing. What you can see in the video is a real-time dicing of facet cuts in our material as the saw moves around the wafer. It takes a couple of hours to process a full wafer into multiple chips, and the process is pre-programmed and automated to run itself once the wafer is aligned. What we can achieve with our ductile dicing process are ridges with a 0.29 nanometer surface roughness in a single pass. We've tested this and it's the same surface roughness achieved with a standard lapping and polishing machine. We measured both with a MgO white light interferometer, and the polished surface gave 0.26 nanometer roughness, showing the high optical quality of our cuts by comparison. Our process is done in a couple of hours for a full wafer of chips, and as it's automated, we've removed most of the manual handling associated with mechanical chemical polishing. This enables ready scale up to higher volumes. The ridges shown in the SEM image are approximately 12 microns wide for 1560 SHG, with machined ridges as small as 3 microns wide without any issues. If you look at the reference paper, this gives full details of our process and setup. To optically characterise our 1560 ridge waveguides, we use a tunable telecoms laser and EDFA focused into the waveguides with a zoom collimator. The spot size and crystal temperature can be tuned for optimal launch and phase matching temperature. We measure the pump before and after the crystal, both on and off phase matching, the SHG output and the wavelength spectra of the waveguide. This allows us to calculate the coupling and conversion efficiency of each ridge. What you see here is an example measurement of 4 ridge waveguides of different widths on a single waveguide chip. These range from 11.5 to 13 microns wide to give some flexibility when choosing the pump wavelength and launch conditions. The uniformity of the sync squared profiles and side lobes indicates high uniformity along the entire 40mm waveguide length. This profile becomes distorted if there are variations in indiffusion profile or ridge width, which can be used as a useful feedback tool for the fabrication process. The interesting thing about our waveguides is that the refractive index change caused by the zinc indiffusion is relatively low, giving us a large 10 by 10 micron mode field diameter at 1560 nanometers. This 10 micron mode size is an excellent match for standard 1550 single mode fibers, which allows us to achieve over 80% coupling efficiencies to the structure by either lens launch or fiber butt couple. This is important as it gives us options for packaging. The 780 nanometers that's generated by the PPLN is also single mode due to the phase matching conditions in the waveguide, although the structure itself can support multiple modes if you were to launch at this wavelength. So, we set out to make PPLN waveguides that can generate more than 1 watt of 780 nanometer output power for use in rubidium traps. What we have here is a summary of our waveguide characteristics of interest as identified by our quantum research projects. The top level figure of merit is that we can generate over 2.5 watts of 780 SHG at over 70% efficiency. You'll see from the graph that we've achieved 2.5 watts of 780 SHG from 3.4 watts of launched 1560 pump in a 40mm long waveguide. This equates to 73% conversion efficiency in the crystal at the top end. In the linear regime, we're getting 100% per watt normalized efficiency before pump depletion starts kicking in around 1 watt pump. We've tested these chips for over 1,000 hours at these power levels with no signs of degradation. One thing to note is we've yet to find the actual ultimate power handling for these waveguides, as we run out of EDFA power to launch, so higher power tests are still planned. If you'd like more details about the experiments and our results, please look at the Optics Express paper in the link. Taking the PPLN crystals one step further, we're working with Covesion to commercialise these devices for sale to quantum research groups worldwide. What you can see here are Covesion's fibre in free space out and fibre in fibre out modules, which are packaged with our waveguides inside. The graph shows power scaling of the fibre in fibre out module, showing 3 watts 1560 input generates 1.5 watts of 780 out. This is measured fibre to fibre, so the whole module efficiency is 50% in this range. We've tested the waveguides for radiation hardness with no adverse effects, and next we'll move on to testing the complete modules for use in harsh environments. Having the waveguides in this format hits the power and usability targets set in our Innovate UK projects, making the waveguides easy to use and ready to integrate into larger quantum systems. And to finish off, we're not just developing waveguides for rubidium trap applications. Our next target is waveguides for blue UV atom traps in calcium, strontium and terbium, And what you can see here is our first result of blue generation at 390 nanometers using a 2 micron period waveguide with a 7 micron bridge. This prototype device generated around 1.5 milliwatts at 390 from a 200 milliwatt Thai sapphire pump laser. We're currently optimizing this and will be reporting on it in future talks. This brings me to the final slide. I'd like to thank Covesion and the Royal Academy of Engineering for sponsoring this work. If you have any questions, please feel free to contact me at the address given on the slide. I'm Corin Gawith from the University of Southampton, and thank you once again for watching.